Number 25 on the AMC 12B. Now this problem actually seems really tricky, but has a really nice and clever solution. Okay, so we've got three concentric circles, meaning they all have the same center, with radii of 1, 2, and 3. As you can see, I've drawn the circles over here. We have an equilateral triangle of side length S with one vertex on each circle. Okay, that's a really interesting condition. So let's see how we can try and draw that. So maybe we have one vertex here. Okay, then maybe we have to have like one vertex around here and then something like that, right? See, this is like roughly equilateral. And we're trying to find what is the side length squared of this equilateral triangle. And whenever you see this, just we basically find S and we'll square it, right? It's not too much of an issue there. So how should we go about finding S? So let's draw our sides, right? We haven't even done that yet. So that's side length 1, side length 2, and side length 3. And we're trying to find the side length, of course. So let's draw the radii, right? We have to always connect our important radii here. So let's draw this radii as 1. I should use a straight line 1. 1, let's say that's 2, and this is 3. And let's just zoom in a little bit on this just so we can really focus. So 1, 2, and this one is 3. Okay. And we're trying to find this side length, right? So look here, 1, 2. I mean, it's almost like if we had this angle, it would be perfect. We could just use the law of cosines, right? We really hope to find this angle, say. So then we would just do 1. If we could do that, then we would easily be able to find S, because then we just apply the law of cosines. But knowing this angle is not that simple. But what are angles that we do know? We do know that this angle is 60 degrees, this angle is 60 degrees, and this angle is 60 degrees as well. So in order to go about finding the angle theta that we really want, we need to try and maybe use a 60-degree angle somehow, right? We know maybe we have some interesting properties, right? Okay, so the key thing here is we know that if we have 1 and 2, we can use law of cosines with this angle. How can we maybe use this 3 side length here? There's actually something really interesting. Like we know these angles, the angles of the equilateral triangle. We're trying to find this angle. What would be a really nice thing that would help us out here? And this is something you have to look for in these kind of, harder geometry problems that really help us. Cyclic quadrilaterals. Yeah, cyclic quadrilaterals really can help us here. And so what if this quadrilateral was cyclic? Well, then this would be 60 and this would be 120. And that's really nice. We just use the law of cosines from there pretty straightforwardly. But how are we supposed to know it's cyclic? How can we actually see? Is it really cyclic? Well, here's something really nice here. We can use Ptolemy's theorem. So Ptolemy's theorem states that the product of the opposite sides, sum of that is going to be equal to the product of the diagonals. So 2s plus, so 2 times s plus 1 times s equals this quantity here, s times this, which is 3. And this holds true. And this Ptolemy's theorem goes both ways. If you have a cyclic quad, you know this sum of product statement will be true. If you know the sum product statement is true, like we just saw here, this statement is clearly equal. So we know this quadrilateral is cyclic. And that gives us so valuable information. Because if this is 60 degrees, then this is 120 degrees. So now we just use the law of cosines, 1, 2, and 120. So 1 squared plus 2 squared minus 2 times 1 times 2 times cosine of 120 equals s squared. And we're looking for s squared, so this is nice here. We just find the top. So that's going to be 1 plus 4 minus 4 times cosine 120. Cosine 120 is, imagine the unit circle. It's going to be around here, so you can see here negative 1/2. Right? So negative 1/2 equals s squared. And this is just 1 plus 4 plus 2. So s squared equals 7. So the answer is 7. And yes, really the key idea here is kind of making a leap of faith here. So we're trying to find this angle. It would be nice to find that angle. And a really nice property that can make this simpler is the cyclic quadrilateral. And we can see that to be true from Ptolemy's theorem. So that's really the key idea here. And something else I wanted to show, one other way you can maybe analyze the cyclicity is, if this was cyclic, then we would have that this angle is 60 degrees and this angle is 60 degrees. And then if you actually do law of cosines on 2, 3, and then 1, 3, you'll get that they're exactly the same. So that's another way you can figure out that why the cyclic actually does work. So yeah, that's it, and hope you enjoyed this video and found this informative. Thanks for watching.